Nice to have Tom Benhamou, Rutgers, who's going to tell us about the point of that spectrum.
Thanks, Spencer, and thanks everyone for coming. It's a pleasure to be in Toronto, see how Setter is really live and forwarding here. Yeah, today I want to talk about these two notions that I came across. And I studied the cofinality of ultrafilters and some problems that are not necessarily related to ultrafilter, but to general partially ordered sets. So let me start with some basic notations and definitions. So throughout this talk, kappa is a regular cardinal greater or equal than omega. I'm almost certain that all the occurrences of kappa are indeed when kappa is regular greater or equal than omega, but I might be wrong. Okay, so given two sets x and y, we know that we say that x is subset star included in y, almost included in y, if from a certain point x is subset y, so x minus y is bounded in kappa. For omega, obviously this means finite. So given a filter f over kappa, a subset of the filter is called a subset base or subset star base of f if every x in f contains an element or contains star an element from B. Okay, that's a star base or a subset star base is a subset base. And the basic question is, well, given a filter f, forget about the ideal. Given a filter f, what can we say about a subset or subset star bases for f? How do they look? So that's not a precise question. So here are a few ways you could interpret this question. So one way is talking about the minimal cardinality of a subset or a subset star base of f. Usually it's the same thing. Kappa to the left and kappa equals kappa, then it's the same number. This is called the character of f or cofinality of f. So another way of thinking about it is maybe a more precise question is what kind of other isomorphism types of can be realized as a base for a filter f. So this is a generalization of a notion of if you know what the simple P lambda point is, it's a notion that Kuhnen considered. So given a directed set D, we say that f is a simple PD point if it has a subset star base such that f has such that B with ordered by the reverse inclusion is isomorphic to that. Okay, that's a simple PD point. So one particular interesting case that will be considered here, we'll also consider general D, but one more famous case is when D is just a cardinal, a regular cardinal lambda. And then a simple PD points just means that you have a decreasing sequence modulo bounded that generates of length lambda that generates the filter.
Characterize the P point, the classical P point.
Yeah,
in these terms.
It's exactly those which are simple PD points for D, which is sigma direct.
Arbitrary. All
Yeah, yeah. So another way of thinking about of like analyzing what the base of f or f star looks like is to think about the Tukey type of either this the relation f with reverse inclusion or f with reverse inclusion star. We will be mostly interested in that kind of Tukey type. I know you probably don't know what Tukey type means. This is the next slide. Okay, so let me define what the Tukey order is and what do I mean by Tukey type, and then it will make more sense. Why is that one way of analyzing generating sets for filters or for posets in general? And note that these questions, I mean, I'm talking about the generating set for a filter, but I could think about also any directed set P and think about a cofinal set in that order. All of these definitions, they basically talk about this kind of situation. And indeed, I mean, we will use these definitions for a general poset P. I mean, not the subset star, but just, okay. And most of the results I'm going to present today are about not general filters. There's just some results about filters, which are not the main point, but most of the results are about ultrafilters. And I'm skipping this part, but there is some external motivation to study this type of thing. They arise from topology or from model theory, for example. Derive intuition, motivation from there. So let me tell you what the Tukey order is. Definitely some of you know what it means, but not everyone. So let P and Q be two partially ordered sets. We say that P is Tukey below Q if there is a cofinal map from Q to P. So cofinal map are thought of as a kind of projection. So what do I mean by cofinal? I mean that every cofinal subset of Q is mapped by this cofinal map to a cofinal subset of P. That's a cofinal map. So it reduces every cofinal subset of Q to a cofinal subset of P. So in some sense, the cofinal subsets of P are simpler than the cofinal subsets of Q. And again, cofinal means, I mean, want in sometimes in forcing theory it's called dense, or there are other.
Pretty weak notion of projection, right?
Yeah, we don't require that. I mean,
No order preserving. No.
yeah, no order preserving. Although,
In the case of ultrafilter, you can assume
yeah,
without loss,
yeah. So whenever in the cases we will be interested, these maps are going to be weakly monotone. So if A is below B, then F of A is below F of B, not the other way around.
In this case, you don't need to definition, you don't need to quantify all substance. You just simply say there's a monotone map with cofinal range. So much simpler.
So we say that two posets are Tukey equivalent if they're Tukey below each other. And when I say a cofinal type or Tukey type, I mean an equivalence class in that relation. Okay, so there is some duality here, which is convenient. It's due to Schmidt, I believe. Not very hard.
It's been tricky, but Schmidt was the first one to
Claim it.
claim it.
Okay. Okay, so there is a cofinal type going from Q to P if and only if there is an unbounded map going from P to Q, where unbounded means kind of the same thing. An unbounded subset of P is mapped to an unbounded subset. And there is okay, I'll get to it in a second. So there is a family of kind of significant cofinal types, which we usually compare posets with. And these are these sets. Yesterday I learned that they are called stacks, right? So someone's, or I've seen people call them standard Tukey sets. But these are just like subsets of a cardinal lambda. They have cardinality less than mu, ordered by inclusion. And the reason they are important is because in most situations, so for example, if the character of this poset is lambda, so we can think about the situation that mu equals omega, for example, or if lambda is a regular cardinal, then mu equals lambda. Then in both these situations, you get this equality. Then what you get is that this is the maximal class among all, a maximal Tukey class among all less than mu directed poset of character lambda.
So, but isn't there a better way to say it? So basically, if you don't assume that this character is lambda, you're just saying that it's above everything that is of size lambda, which is less than mu directed. Isn't that the case?
I'm not sure it's true in general. I mean, I don't know. This is what we were talking about.
Okay, okay.
But this is, I have this assumption because
Okay.
I think its situation is not completely clear. But there is also a, in that situation, there is also a combinatorial characterization, which says when if you have a directed set P, so to be Tukey above lambda to the less than omega, this is going to be, again, under that situation, and then, so. Assume that, then this is equivalent to saying that to the following combinatorial property of P, that there exists a sequence of alpha of lambda many elements of P, such that whenever you take mu many of them, then the collection P alpha alpha in I is unbounded. Okay, so that's going to be equivalent. In one direction is it's you don't need any assumption. Right? So if P is Tukey above that, then you take any unbounded map from this to this, and the P alpha are just going to be the image of the singleton. And then you can check that this holds. The other direction is also not very hard once you assume that, but it's we don't know what's going on in general. Okay, so a subclass of the above is the in fact the regular cardinals, because lambda is Tukey equivalence to lambda to the less than lambda. Okay, so whenever I'll state something about lambda to less than mu, it will also apply to just plain regular cardinals. Okay, so now the two definitions that appear in the title. So what is the point spectrum, or sometimes we call it the Tukey spectrum? It's the collection of all regular lambdas which are Tukey floating. So we can think about it as all lambdas such that there is a sequence of lambda many elements in P, such that from any lambda many of them are unbounded in P. Okay, so that's the point spectrum. And the second one, which I don't know if it's a standard, I haven't seen them elsewhere. It's not but this is the depth spectrum. So the depth spectrum of P consists of all regular lambdas, such that there is a lambda tower in P. So what's a lambda tower is just an increasing sequence in P, which is unbounded of length lambda. You can think about it like how far can if I start constructing an increasing sequence inside P, after how many steps will I get stuck? Like you have several options for that process to happen, and all these options are going to be exactly the lambdas which are in the spectrum. Okay, so we'll see how they come into play in a second, and they relate to cofinal notions of P. So some examples, you take P to be C to the less than omega, then in this case, it's known to be like the maximal, as I said, it's the maximal class of all poset of cardinality at most, the directed poset of cardinality at most continuum. So you get every regular cardinal, in particular, you get every regular cardinal in the interval, omega and C, but the spectrum, the depth spectrum is omega. you have any increasing chain of sets, then you get stuck after omega many steps. Okay, a product. If you take a product of just two regular cardinals, you get that the spectrum is the depth spectrum, and it's those two cardinals. In general, both the spectrum and the depth spectrum are basically the spectrum of the product is the union of the spectrum, and the depth spectrum of the product is also the union of the depth spectrum. You get that. So, for example, we to see a situation. So if you take that product, then this omega 1 get absorbed in this interval, but you are adding omega 1 to the depth spectrum. Okay, well, just some example just to see these notions in motion. So some easy observation. So if P is a directed set, then the depth spectrum is always a subset of the Tukey spectrum. And the reason is, well, the tower is going to witness. It's going to be a witness for that property. Okay, another observation is that the soup of the Tukey spectrum is always bounded by the character. So that's a kind of a pigeonhole argument. You take any lambda which is greater than the character, lambda regular greater than the character, then whenever you give me lambda many elements, I can find one element of the base which gets above lambda many of them. So they're going to be bounded, right? So any lambda above the character is regular lambda above the character is not going to get into the spectrum. And also there is an argument to show that it has to be the case that the cofinality of the character is an element of the spectrum. It's not a part of the argument. So in particular, you see that whenever this is a regular cardinal, then it realizes the maximum of the spectrum. Okay. And Isbell showed in his 65 paper, I think, that suppose that every singular cardinal is strong limit. So under certain cardinal arithmetic assumptions, even if the character is singular, you still get it to be the supermode of the Tukey spectrum. Well, I didn't ask the question, but a natural question to ask here is whether it's a ZFC. It's just a ZFC fact that the character of P is the supermode of the spectrum. And so
If he was a set theorist, he would ask that.
definitely, yeah. But he was a category theorist, right? That's so then the way I encountered this situation and started to dig up the history of this problem was trying to understand again the character of the notion of a character of an ultrafilter through the ultrapower. So let me recall set up some basic definition for the ultrapower. So let U be an ultrafilter over a set X, and let JU from V to MU be the usual ultrapower embedding. So MU consists of all equivalence classes of functions from a domain is X, a modulo the ultrafilter. JU takes X to the equivalence class of the constant function X. And here I'm not assuming any type of completeness of the ultrafilter. So, I mean, the ultrapower might be ill-founded. Okay, so I'm not, you can have non-standard elements. It's okay. And so what I did was to kind of characterize this this notion when does an ultrafilter get Tukey above that in terms of the ultrapower. So that was the purpose of this theorem. So let U be an ultrafilter over X and assume again this assumption. Oh, I wrote cofinality, but the typo. Then the following are equivalent. U is 2k above lambda to the less than mu. And we get some sort of nice covering of the pointwise image of lambda. So mu has a so-called mu thin cover for the pointwise image of lambda. What do I mean by that? There is an element of the ultra power which covers the pointwise image of lambda. When mu is not a transitive model, then we need to explicitly say what we mean here. So I mean that for every I less than lambda, mu models that ju of I is an element of X. Now that makes sense. That's an element of the ultra power. That's now. And so that's mu has a certain cover for ju of lambda. Of course, there are covers for ju of lambda. You can just take
This epsilon there is not epsilon, but epsilon u.
yeah, the epsilon that mu thinks is
Epsilon. The index u, I guess.
yeah.
Because otherwise you put epsilon, you're set theorist and you take the.
Yeah, if your model theorist, like this is the relation which is interpreted in the model. Well, okay, yeah, I will put the U here. It's for the well-being of it. Okay, so, oh yeah, so obviously there are sets like that. There are always sets like that we satisfy that. You can just take ju of lambda to be X, right? But so we need some kind of a non-triviality requirement about what X, and this is the mu thin, the cover being mu thin. So it just means that the cover does not contain the image of a set of size mu. This is what it says. So for example, if X would have been that, yeah, it would have contained the image of a set of size mu. Okay, so that turns out to be equivalent. And for me, this is an ultra-power characterization for being 2k above lambda to the less than mu. So covering the pointwise image of lambda is something that comes up a lot when studying fine ultrafilters, for example.
So can you say something more about the motivation? Because, okay, so we're talking about ill-founded ultra powers.
Yeah.
So you have to say, why would you care?
So I care about sigma complete ultrafilters. That's
Okay.
yeah, and I mean many of the orderings which we have on ultrafilters, for example, the Rudin-Kistler ordering or the Rudin-Frulich ordering, all of them have very useful ultra power characterization. The 2k order doesn't seem to have one. Well, that is so. In fact, this is. I didn't say it, this is the next thing. In fact, that theorem is a bit more general. It characterizes the 2k order.
Okay.
This is just a byproduct of it.
Okay.
And one more question that comes that this is maybe what I should have started with is it's unclear what the character of an ultrafilter means in terms of the ultra power. You look at the ultra power of an ultrafilter. Clearly, it should be an invariant of the ultra power because anything which is invariant under the Rudin-Kistler or isomorphism is an invariant of the ultra power. So the character should be something like that. But when you look at the ultra power, what is it? And I think this, as you will see in the corollary, this gives you the that sensation maybe. So in particular, when we take lambda equals mu, then this characterizes the 2k spectrum, right? So the 2k spectrum is exactly all those lambda for which there is a lambda thin cover for the pointwise image of lambda in mu. So if it would be the case that the sup of the 2k spectrum of u is the character of u, then you have a character. You understand what is the character of u in terms of the ultra power. But as I said, this is unclear. So that's the question. Is it a ZFC fact that you have equality? So this is open. I didn't solve this, but there is some progress on this, which is the following theorem, that although it's not necessarily, we don't know that equality holds, we do know that the cofinality of the supremum of this spectrum of the 2k spectrum of P must be an element of the 2k spectrum of P, which is kind of the same thing you had for the card. It also was the case. So for example, the supremum of that cannot be arbitrary. It has to be already an element of the spectrum. And I think what's interesting here is not just the relation, but the proof. The proof kind of uses PCF theory. And the reason it uses,
Why do you there you put arbitrary P, do you?
yeah, it's for arbitrary.
Indirect.
Oh, you're right, sorry. For directed set. That I should have been more precise, I'm sorry. Yeah, and the reason PCF comes in naturally is because, okay, we know this equality is going, this equality is going to be true already when this is a regular cardinal. And if also, so the only case which is interesting is the singular cardinal case, for this question at least. But also if the sup is a regular cardinal, yeah, I mean, there should like most of the cases where the sup is a regular cardinal, we know how to deal, at least when the character is a regular cardinal. But yeah, there is still some progress to be done when the sup is a regular cardinal. So we didn't solve this case completely. This is maybe what's missing to get the full result.
So to understand this. So if this sup is inaccessible,
Yeah, so we don't know what's going on when it's inaccessible. So and okay, so let's prove the theorem. So the theorem follows from the following lemma. The lemma shows that if lambda, which is an accumulation point of the spectrum, such that and it's a singular cardinal whose cofinality is not in the spectrum, then you can produce something above lambda in the spectrum. So it's not going to be the max, the sup, right? So this is what it says. If lambda is an accumulation point of the spectrum, and it's a singular cardinal, and the cofinality of lambda is not in the spectrum, so it doesn't satisfy this assumption, this conclusion, then you can produce a new point in the spectrum. So definitely the supermum doesn't satisfy that. So you get the theorem. Sorry? It should be P. U is an ultrafilter, because I think about ultrafilter, but it should be P.
so moreover, I think the correct to say that Isbell's theorem false. Somehow, because it's going to be a strong limit.
I don't see.
Strong limit, and then you are simply saying there's something. No, it's as strong as Isbell's.
I don't see how it's strong, like that. The T-Bell's problem follows just by not problem. Yeah, theorem. It follows from just adding the cardinal arithmetic assumption that he has. Right. Okay, so any question about the formulation of the lemma? Okay, so let's start with the proof. So just I'm gonna black box something from PCF theorem. But they can be found in the, for example, in the Abraham and Magidor chapter in the handbook. So what is the PCF of a set of so you have a set of cardinals A. We usually assume it's progressive. You will see what it means in a second. But you have some set of regular cardinals A. So what is the PCF of A? So basically you study this structure. You take the product of those cardinals. So functions which at a given cardinal, they output some ordinal below that cardinal. And you order them modulo an ultrafilter D, and you take the cofinality of that. And you range over all possible ultrafilters. So you get many different cofinalities. And that's the PCF of a set of regular cardinals. That's the definition. Obviously, that's a linear ordering because D is an ultrafilter, so the cofinality of that is going to be a regular cardinal. And therefore, the PCF of A is always a subset of it's a set of regular cardinals. Okay, so that's the lemma again, so we don't lose it. So let's start with the fix any x. So we have this lambda, fix any x which is unbounded in lambda, and it has order type, the cofinality of lambda, and assume that also x it should be the other way around. Sorry. The minimum of x is greater than OTP of x. Right, so I can chop x from high enough so that the minimum, and this is what we call the progressive set, and I want x to be unbounded in lambda. So for each row in X, now we have, we know in particular that row is going to be in the Tukey spectrum. So we fix a witnessing sequence for that. Okay, so we will have a lot of, so here we have X, so we have some regular cardinals in X. And so we have, I don't know, row 0, row 1, row 2, and here we have lambda, and for each one of them we fix a sequence denoted by rows. And also row 1 of 0, row 1 of 1. Okay, so we have all of them, and each row here has the property that whenever you take a subset of it, of the cardinality of its row, it's unbounded. That's the property. Okay, so now we come to the PCF black box. So now there are some sets which are called the PCF generators.
What is a tower?
Well, this was done by,
What is what? Sorry?
Tower.
Oh, yeah.
I don't think it was
Sure.
this machine.
Yeah.
It's not a tower, it's a tower. I'm sorry.
Machine.
But maybe like they call it a tower. It's
First tower of the towers.
It's a noble
Eden-
towers as well.
Isn't that how like mouse started? Like the notion of a mouse from inner model theory?
Mhm.
Like they made a typo?
I don't think there was spine checkers back then. Not
This
that
is what I
many
heard,
ones.
that there is a typo okay,
What did they
anyway,
try
I
to
meant tower.
What did they try to write?
Tower.
No, I mean for mouse.
Nice.
Nice, maybe. Yeah, it's an unfortunate. Okay, anyway, what I mean, let me just say what these are the PCF generators. So we have
There's
B
only one
theta.
common letter. I don't know.
Row is that,
No, and okay, let me just write whatever. So we have this beta B sub theta in the PCF of X. These are some subsets of X. And then we have these ideals, the tower of ideals, J less than rho for any cardinal row. So it's not the same row as above, I should. But let me write it here. So J less than, I don't know, tau. Tau is any cardinal. And we have these sets B theta, where theta is just something in the PCF of X. And these form a tower. So if tau 1 is a subset of tau 2, A is less or equal than tau 2, then J less than tau 1 is a subset of J less than tau 2. and they are continuous at limit cardinals, and the following things hold. The union is all the power set. And each such ideal is generated by the PCF generators with theta below that row. And if theta is in the PCF of X, then I wrote TCF, I'll tell you what it means in a moment, of the product B modulo J less than theta equals theta. So if theta is in the PCF of X, this means that there is an ultrafilter on X such that the product of X modulo that ultrafilter, the cofinality of that is theta. What this means is that it actually can be realized, this using taking the product of that particular set, modulo not an ultrafilter, but an ideal. So when you have an ideal, it's no longer a linear ordering. So what do we mean by that? So the TCF means it has a cofinal subset which is linearly ordered, and that's and the minimal size of such an a sequence is theta. So this is what we mean by TCF. TCF means that there is a linearly ordered sequence with minimal, and then the minimal length of such a sequence is theta. Okay, so these are this is the black box in it from PCF theory. Now back to the proof. No, so I let mu be again, it should be X here, be the minimal such that the PCF generator is unbounded in X. So maybe some of them are bounded, maybe, but from a certain point, they are unbounded. And let mu be the least such element in the PCF of A, and know that by minimality of mu, then J less than mu being generated, and all of these sets, they are particular, like for every mu prime less than mu, B mu prime is an element of J less than mu, so it's bounded. Okay. And any element here is going to be bounded. That's also important. I mean, they're just bounded because it's the minimal, not because of what I've just said. But the fact that this ideal is a subset of that is by minimality, and the fact that they generate it, and by should be by 3. I added a bullet. So by 3, we can fix a scale. The scale, again, it's increasing and cofinal in that product, modulo the ideal. And we know that mu has to be at least lambda. Otherwise, since if mu is less than lambda, then first note that this, we already noted that this is a subset of the bounded ideal, but then also B intersection mu is something which is bounded in lambda, and then if you remove from B mu, you get something which has to be positive with respect to that, because B mu itself is unbounded. So B intersection mu is definitely bounded. So if that wouldn't be positive, it would be here, so it would be bounded as well, and then B would be bounded. Okay, so it must be the case that this is positive with respect to the ideal. Okay, so now I have this positive set, and I can define a function on a positive set for which we just take the pointwise soup of each element in the scale. And this is defined on a positive set. I mean, otherwise just define it 0. It's not really important. But then what's happening here is that G is going to be an element in that product. So since this is a scale, it's supposed to be, and note that for every I, G is going to be greater than Fi of B on that positive set. So it's not bounded by any of these functions, and that's impossible because that's a scale. Okay. So mu has to be greater or equal than lambda, and in fact, greater than lambda because we assume lambda is singular and mu is regular. So that's the first part of the proof. And from now on, we're just going to talk about combinatorics of scale, but all I did so far was to produce this ideal, say it's included in the bounded ideal, and concluding that mu has to be greater than lambda. Okay, this is what you need to remember.
But in some sense, you did not use much of your original assumptions.
I don't.
You see, you want to, okay, so you have this mu, which is the mu log is bounded. You are doing all this stuff just to show this mu is above lambda.
Yeah.
But this is a general fact. What I want to say, did you actually use the fact that you had a situation?
The assumption of the lemma?
I mean,
What, that it's
we'll see, it's coming, must be coming.
Yeah.
But this whole setup seems like it could happen from this J lambda bounded ideal rather than thinking about the whole tower.
but I do want to realize the value of the PCF. So can I realize it with the bounded ideal always without any further assumption? So this was my problem. I originally did it with the bounded ideal. I didn't want to go into PCF theory, but then you cannot just show in ZFC that you can always realize an element of the PCF with just the bounded ideal, no? Like the most general setting, maybe in concrete situation like Aleph Omega or something, you can, but I'm not sure about the general.
I'm still wondering about the BU. So why is there a BU which is unbounded in lambda?
Oh, yeah, so that's a good question. But if all the B mu were bounded in lambda, then someone X would have to be bounded in lambda because of that equality.
Oh, powers.
Yeah.
Oh, I see. Yes.
Yeah, but that's a good question. Okay. So let's continue with the proof. Yeah, so the goal is to show that that mu is also in the Tukey spectrum. Okay, this is what I want to show. So remember, I have this scale.
Does this actually show are you using the map? Anyway, so I'm going to further, I'm curious how many of the moments you can get in satisfaction. One in this one.
That's
Or,
I don't. It's important. The minimality somehow important because I need it to be the bounded ideal somehow. So I have this scale f alpha less than mu. Now, what does it mean that I need to show that mu is in the spectrum? I need to produce mu many elements such that any mu many of them are not in the. So how am I going to produce them? I take any of these functions. There are mu many of them. Fix any of these. So each such function, it's for each element in, now we have this B here, which is a subset of X. So I only consider those in B, and for each one of these elements, it gives me an ordinal below it. So it points to one of the elements in the sequence. So it kind of each F0 would say would pick this element, this element, this element, I don't know, some elements. But how many elements does it chooses? It chooses the order type of B, many elements, which is not in the Tukey spectrum. This is my assumption. So what does it mean that it's not in the Tukey spectrum? It means that you can find a subset of these conditions which is bounded. Okay, so this will produce. This is what produces my. So say f alpha is the red function that picks this one. This produces p star alpha here. And now another function picks, I don't know, this one, this one, this one, and whatever. And this is f beta. Then again, I apply the fact that theta is not in the spectrum of P to say that an unbounded subset of theta from these elements must be bounded by some condition, by some element of the not of the forcing of the poset, sorry.
But the bounded sets might not be in your ultimate filter.
Not in the ideal, just unbounded. Yeah, you're right. I don't know anything about, I just know it's unbounded, and therefore it's positive with respect to the ideal. That's the point. Right, they're all unbounded in theta. Mu was chosen so that it's a subset of the bounded ideal. So whenever I take an unbounded subset, it's going to be positive for that ideal. Okay, so these are this is what we do here. So repeating what I just said, there is some I beta of size theta such that the sequence indexed by f beta of rho is going to be bounded by p star of beta. And we claim again that the sequence of these conditions, they are going to witness the fact that theta is in the Tukey spectrum. Okay, so otherwise, so there are many of these which are bounded by a single p star. So there is a single p star which is bounding many of these guys, many of these guys. Each one of them in turn bounds many of these guys, and we hope that this one will actually bound for some rho, it will bound rho many of these guys. And this is the claim. The claim says that there is rho in B such that the set of indices such that beta is in I, so the set of indices where P bounds P star beta, and rho is in I beta, namely P star beta bounds F beta rho, a P sub F beta rho comma rho is unbounded in rho. This is what we claim. It's a translation of that. This set here, this set, the set of F beta rho, beta is in I, rho is in I beta, is exactly the set of indices. And so it's not exactly, maybe it's included in the set of indices I less than rho such that Pi rho is below P star. So you see, if we show that this has size rho, this means that there are rho many elements which are bounded by the same P star, and that's a contradiction to the choice of those sequences. Okay, so all it remains is to show that this set has size rho. Okay, so let's go for this. Otherwise, again, for each rho, this is bounded. So it is bounded by some rho, alpha rho. There are questions?
No, can't see the screen. I mean, you see.
Not automated?
They're not complaining.
You're showing that board, not that one.
Oh, I think you can see, I mean, it's,
Oh, I see.
oh, I see.
Yeah,
Yeah,
because
yeah,
it's-
I guess. This is, this is what you asked for.
yeah.
Okay.
I mean, okay, so is it clear what I'm trying to prove and why does the claim finishes the theorem? Okay, so again, we assume otherwise. So assume that each one of these sets for each rho in B, this is bounded. So there is some bound alpha rho below rho. This describes a function defined on B, right? And the function f alpha equals alpha rho is then bounded modulo that ideal by some element of the scale, f beta. And since I is unbounded, I may assume, because it's increasing, right? So I may assume that this beta comes from I. Okay, so at least this thing, beta in I can make sure that this holds because I is unbounded and it's a scale, so it's increasing. Namely, f beta is about this f of alpha rho is alpha rho, modulo that ideal, and in particular, it's above it in the bounded ideal. This is all I needed. All the PCF preparation was for this part. So f beta is mod bounded, it dominates F. And since I beta now is unbounded in lambda, that's actually type, should be theta. I mean, I betas are subsets of theta. It's also unbounded, actually, it's also unbounded in lambda because it's not a mistake, but it's so I beta was chosen to be in B theta, and B is a subset of lambda of order type theta. So I beta is unbounded in lambda. Then there is some rho beta in I beta on which this happens, right? So because this is the bounded ideal, this is unbounded, so we can find a point of intersection. Okay, and this whole, but this doesn't work with the way we define F. F is supposed to bound F beta on this point. I mean, tracing back the definition, you just see that on one hand, we know that this holds. On the other hand, since beta is in I and rho beta is in I beta, you have the other inequality, and that's a contradiction. Okay? And the rest of it is what I said it in the beginning, so let's repeat that. So now that we conclude this lemma, we fix a row as in the lemma for which this set is unbounded. And therefore, this must be unbounded because this is the property of the original sequence, that whenever you take a subset of rho which is unbounded in rho, this has to be unbounded, but on the other hand, it's going to be bounded by P, and that's a contradiction. Okay? So that's the theorem. And I think kind of things around the singular cardinal, I mean, questions about singular cardinals in the context of the Tukey order, it's, I think, quite natural to look at the PCF tools. So this is just one example. And I think, I mean, I didn't continue with it yet, but there seems to be more going on here. I don't know what time it is. You guys exhaust all my time already? Oh,
Until 3.
and what time is it? 2:25. Oh, okay. Maybe I'll see. Okay, so back to the notion of the Tukey and depths. So remember, Tukey is all the lambdas which are Tukey below P. The depth is all the towers. So now we are worried whether, so when we consider an ultrafilter, we can think about the subset or the subset star, but beside the kappa, this is going to be the same thing. So it doesn't matter which one we pick. And just some other information about this stuff. So the pseudo intersection of U is, I mean, should be the minimal size of a collection in U which doesn't have a measure one pseudo intersection, right? Well, that's going to be in the next lemma, but we can define it as the minimum of the Tukey spectrum of U. And the depths, it refers to the tower number. Obviously, this is really by definition. And yeah, so the beginning of this theorem just says both of them. It's not a hard theorem to prove. It's pretty easy actually. That P of U is indeed the minimal size of an unbounded family in this, and tau of U is, by definition, is the minimal size of a tower, and that they are equal. So, like in the spirit of Maliaris and Shelach, for ultrafilter, the proof is much simpler. That's not much to do here. So this is something to keep in mind, that it has to be the same thing. And let's give again.
Sorry about, can you, so the tower means is decreasing, but there's nothing in
Measure one, yeah. No, measure one.
but you see, you could have all the same sort of numbers. I'm particularly interested in the number P.
Yeah.
You could have a P, which is so that there's no positive cetera to the bounded. Yeah. if you go to, if you look at omega.
Yeah, this is like a pi p. This is
Yeah,
we have
if you
this.
look at the case of omega,
yeah.
you can have a sense of P of like ultrafilter U. So this is the minimal correction of omega, which has no infinite pseudo restriction.
Yeah, so this has a name. It's been this is what they call pi p of u. So you don't have like so it's the minimal size of a collection of elements in U.
Anyways, but the point is that the original P that used the original P represented, you use this to define that.
Ah,
You
so
see what
it's,
I'm saying?
you
The
can
quantity
actually
of P can be defined using this P
ultra
of U.
filters. Yeah, yeah. You can always assume that the collection. Yeah.
So I don't know whether you have it here.
Yeah, I think it's
Probably
whether this is
correct. So look at the, of course, there's a natural notion of P of kappa, whatever kappa the group lives.
let's think about omega. So yeah. I mean, I know that Brendel and Sherlock were looking at this type of cardinal invariants for ultrafilters. I can't remember if they said it's open or not. I mean, if this can be separated or not. But there is a paper called very original name, ultrafilters on omega. I think that's the name of the paper. And I think in that paper they studied this, trying to separate this kind of invariants. Or maybe ultrafilters and ideals on omega. Maybe there's also ideals. Okay, anyway, some examples for that. So let's say we start with a model of I mean, the question is how can the spectrum and the Tukey spectrum of an ultrafilter look like? I mean, there is a reason we're interested in it, because as we said at the beginning, it kind of measures how it's a way of measuring how complicated is the cofinal type of an ultrafilter. The more elements there are in the spectrum, the more complicated the ultrafilter is. So how can the spectrum of an ultrafilter look like? So start with the model of say GCH. You pick your cardinal kappa. Kappa, remember, can be omega. Pick your some regular cardinal lambda above kappa, and just add lambda many coins to kappa. Then look in the generic extension. Then over there, every uniform ultrafilter kappa, well, two things will happen. First of all, the Tukey spectrum blows up to be the maximal thing. Okay, so all the regular cardinals come into the spectrum of the ultrafilter, the Tukey spectrum, and it's the other way around. The spectrum PP U, the subset. Suppose there's a missing kappa here. It's supposed to be also kappa. So what I wanted to, so you cannot add things to the depth spectrum that wasn't there already. It wasn't supposed to be there. So I mean, you will have, for example, P points in this model because D equals C or whatever. So for these, you will have that kappa plus is there, but you might not be the case. So I'm just saying include them, but you're not adding things above kappa plus to the spectrum. Okay.
So is this just like Kunin's proof?
Uh,
Kunin's proof that
There are no-
that's the same.
no,
pretty much, right? Yeah.
not exactly, but it's motive
If kappa
definitely.
is omega, I guess that's it. But if kappa is not omega,
Yeah,
then
and
we
also
do
there's
something.
the thing about the ultrafilter. I mean, being inside the ultrafilter,
Right.
but it's very
Okay.
it's very similar in flavor. Yeah,
Right. So you have to fix a name for ultrafilter,
exactly.
and yeah.
Put it in the elements.
Sure.
It's not a great
Yeah,
theorem, I
okay.
know. Okay, so let's recall this thing that if you use a simple PD point, if there is a subset star base B for you, use a simple PD point if you can if you can have a base for U which is isomorphic, which looks like D. Okay, so that's this
Sorry,
motion.
what is D?
D is any directed set. So we fix a
Oh.
directed set, we define what is, this is what we define to be a PD point. And so this is also due to someone, it's more general, it's about linear ordering, but U is a simple P lambda point if and only if the pseudo intersection number of U equals the character of U equals lambda. It's not hard to prove this, but you see in this situation, everything, both the step spectrum and the Tukey spectrum just becomes a singleton. Okay, so in that sense, and it's indeed a simple P lambda point, it's a very simple ultrafilter in terms of cofinality structure. And okay, so from these examples and other examples we have, I mean, we don't see an example of a convex set of regular cardinals. So can it be convex?
I asked myself this question when you started telling number one.
Yeah, so
But you're not taking quotient of, you're just
It's
asking whether each one of them
yeah,
is
yeah.
okay.
You're right. You're right. I need to think of for a millisecond whether I didn't mean a quotient there or not.
It took me longer.
Okay, so this is the question. And we're gonna, I mean, the next theorem in particular answers this, but I think it's a nice theorem that you should see. So this is Echler, this is not me, but it's also generalized, or at least it's an analog theorem for Echler's theorem. So Echler proved that you take any directed set D, which is well-founded in sigma direct. I'm almost positive he also has a proof where you don't assume well-foundedness, but I didn't find it. So this is the way I know this theorem. Then you can there is a CCC forcing extension where you can find a dominating family in omega to the omega, which is order isomorphic to D. You can realize basically every partial order well-founded in sigma directed as a dominating family of functions from omega to the omega. And so this is something we did an analog of that for ultrafilters with my co-authors. And well, while Echler used the Echler forcing, the nonlinear iteration of Echler forcing, we use the Matthias forcing to create our weird ultrafilters with a generating set. So that's the theorem. So it's with James Cummings, Gabe Goldberg, Yair Chayut, and Alejandro Poveda.
You badly misspelled Mr. James's last name.
Who's
You're not, well,
what did I spell wrong? Mine? Or...
well,
Oh no! Sorry, James. I'm very
Is he there?
no, but it's recorded and. Yeah, I'm a lost case when it comes to type.
Okay, 1 out of 4, that's okay.
At least the first name of my family name, I think. Okay, so suppose this is the measurable case. We'll also have a case for omega in a second. So suppose you start with a very large cardinal. I mean, I'm not going to define all this stuff, but you start with a very large cardinal, labor indestructible, super compact cardinal. Okay, and you look in that model, and you let D be a well-founded kappa plus directed poset there. Then there is a kappa plus CC forcing extension where there is a collection of subsets of kappa of cardinality kappa, which a subset star generates a normal ultrafilter, which is also a simple PD point. So this means that if you start with a model where you have labor indestructible single super compact cardinal, then you can realize any D, a simple PD point, or any D which is well founded in kappa plus directed as a base of a normal ultrafilter. Okay, so that's the measurable case, and we also have a version for omega. There's a star there, and again, sorry, James. let D be a well-founded sigma-directed poset of cardinality mu. Then there is a mu star close forcing followed by CCC forcing. So, and usually this one will not appear, and you'll see it for its use, in which there is a simple PD point. And the star is because in the preprint we still didn't update the second one, but
Sorry,
we
Miguel.
did-
So you mean on omega, right? Because you're not saying an odd cardinal.
oh yeah, on omega.
Okay.
Second one on omega. Okay, so in particular, you can realize a small corollary like non-convex sets. Just pick your favorite. You can pick any two regular cardinals, let's say omega 1 and omega 3. There is this theorem says you can realize a p omega 1, omega 3. Which I feel,
You take this product.
Yeah. Okay.
There's some restriction on mu, right? Mu is not omega.
Mu, well, it's sigma directed and
Okay,
Yeah.
yeah, sigma, okay.
yeah, I mean,
Well,
yes, you have to say it doesn't have a maximal element. Yeah, doesn't have a maximal.
Interesting one.
Doesn't have a maximal element.
Yeah.
Too bad, it would be nice to.
An ultra filter is generated by a single set. Yeah, that's
It doesn't make sense to ask for these things at the same time, but for ultra filters, can you get models where you have different ultra filters with, I give you a collection of derivatives.
a great question. So there is a theorem of, for example, of like
Obviously,
what-
there's the Nikos and.
Exactly.
and others.
Nikos proved that if you just want to realize that P mu and P lambda from different mu and lambda, that mu have to be B, I say mu less than lambda. Then mu has to be B and lambda has to be D.
But those are specific, suppose okay, I don't take those.
There's a
I take
question
the
with,
other-
we asked this question in the paper. Can you
Oh.
realize now different one? By the way, Mildenberger and Browninger, they proved the consistency of having a P aleph 1 and simple P aleph 1, simple P aleph 2 simultaneous. I don't think I'll have time to say it, but
That's the famous Blas-Shalla paper that was wrong, right?
exactly,
Yes, okay.
exactly this one.
And it took like 30 years to figure it out.
Yeah, now lately, like 2 or 3 years ago, I think
Yeah.
they published.
It's not.
Hmm?
And the proof is actually not that tall.
The Mildenberger morning, I didn't go over the paper. If you can tell me about it later, I'll. Okay, so my plan was to go over the proof of that, but I don't think I have time. I can tell you kind of the idea. So the idea, maybe, so basically I'm going to do the omega case, the second theorem. And I'm going, now you're going to see where I need the mu plus close and CCC. This is basically to force some diamond. So this is where our proof differs from the original Kuhnen method. So Kuhnen, to create a simple P lambda point, he iterated Matthias forcing, just linear Matthias forcing of length lambda. And then eventually claimed that all the sets that you created along the iteration, that they generate a simple P lambda point. We are not going to do that. We are going to have some nonlinear iteration, but we're not going to take all the sets. We'll have some daimon, which will guide us our which ultrafilter we pick at each step. And then we're not going to take all the sets. We're going to take the sets where the diamond gets something nice. Okay, this is the idea. So we need to force diamond at the beginning. By the way, this doesn't appear in this one because you didn't ask me why don't I need here like but I mean you would expect maybe that this like a component is in here.
You did it already.
Sorry?
You did it already.
Yeah, okay. Okay, yeah. But also, I mean, I need diamond, so this is the point. Diamond will be available above a super compact
Yeah.
in many places.
Mm.
And also in here, right? So if I already have diamond, like the certain diamond I will need on omega, like on not on omega, but at mu plus, then I'm then I don't need that part. Okay, so,
And what is the CCC forcing? So some,
it's a nonlinear iteration of Matthias force.
oh, yes, you said it, yes.
So again, the forcing is going to be a two-step iteration. The first adds a mu plus diamond sequence to points of cofinality mu by initial segments. The mu plus closed forcing. And the second forcing in the extension, it's a nonlinear iteration of filter Matthias forcing based on disordering. You can think about D being, I don't know, omega 3, but basically this is how you think about it. You have mu plus here, and each row, so you have kind of a copy here of D. And the order is the pointwise order, so less or equal in both coordinates. Okay, and so what do we mean by a non? I need a clock. Okay, have some time. Okay, so just to describe what a nonlinear iteration is, so, let me assume already I'm giving a sequence of names of filters. Then afterwards, I'm going to define these name of filters. But just to give you the sensation of what is the nonlinear iteration and what does it do. The basic component is what we call Matthias forcing. So Matthias forcing with respect to filter, the elements are basically pairs A in omega to the less than omega times the filter. Now you can end, so A is weaker than B if B is an end extension of A, so we're approximating a real by a subset of omega by end extension, and B is a subset of A. We shrink the set, the measure one set, and the new elements, they come from the set A, so you can think of this A as sets of candidates for the continuation of the sequence. And when you force that, you generically get a real, and that real has the property that it diagonalizes or it answers every set in F from a certain point. Okay, it's a pseudo intersection for F. Okay. So let's fix a sequence of names of filters, then I'll tell you how I define them. So what is a condition in the forcing? So it's a finite support function whose domain is this mu plus times D, such that whenever you pick a pair, then what do I mean by that? The P restriction to alpha D means basically the cone below alpha D. So you consider only the coordinates in the support of P, which are below in that weird ordering, that pair, alpha D. Okay, so if I'm here at the point alpha D, I only restrict myself to this area. Okay, so less than D and less than alpha.
But am I missing something? So your F alpha D seem to be unrelated. I was expecting that F alpha D is going to be generated by the Matthias field set so
We
far.
haven't said anything about it.
I didn't say what they are.
But it says suppose that they are given.
Yeah. So I'm just,
So you did say something.
yeah, I'm just saying, let me
To be
describe.
defined later.
Yeah, I'm just saying I will first assume I have the filter just to describe what is the nonlinear iteration, and then I'm going to tell you what are the filters. And at coordinate alpha D, you require that the condition, which is which has support below alpha D, forces that P of alpha D is a condition in the Matthias forcing associated to the filter indexed by alpha D. Okay. So that's the nonlinear iteration. Again, the idea is that the generic real we are going to add here only depends on that part of the. Okay, so I don't know, a question, a kind of an example that made sense to me is to think about a product versus iteration. So if you do a product, it's kind of having a linear ordering where no two are comparable, while an iteration is a linear ordering. Okay, that's the difference. Okay. So now I'm defining the filters of alpha by induction of alpha. So I'm going by induction this way. And now given alpha, I'm going to define the entire row. That's the induction. And this choice is going to be guided by the diamond sequence I forced. So assume we have the sequence X alpha, and of course I want them to guessing names. So I'm guessing that the diamond already guesses subsets of H of mu plus. And at stage alpha, at stage alpha, since I already defined all the filters which with index below alpha, the forcing up to here is already defined, not including alpha itself. This is without alpha. This is like open here. Okay, and that's this is the forcing I denote by P alpha D. So now, how do I define my filters? First, trivial cases to avoid. If this alpha is not in the domain of the diamond, just have the filter to be the co-bounded filter. Do something trivial. We're going to ignore such stages anyway. If X alpha doesn't turn out to be a name for an ultra filter for this generic extension, also make it do something trivial. In the third case, X alpha is a name for an ultra filter over that model. Okay, so now I'm defining an intermediate filter, which is the filter. Okay, so I will need to define an intermediate filter here, but now the definition proceeds by induction on D. And this is where I need D to be well-founded. Okay, so what is basically what I do? I take the ultra filter, basically the name for the ultra filter X alpha, and now I chop it in all the coordinates which are below below a certain D. And this is the filter I'm calling F dot prime alpha D prime for D prime less than D. So it's all the names in that generic extension, so that the trivial condition in the quotient forcing forces them to be in that ultra filter. Okay. So this is the filters F dot alpha D prime. So that's a P restriction to alpha D name for a filter consisting of sets which are forced by the trivial condition of the quotient forcing to be in X alpha. Now we have to decide what is F dot alpha D. So you ask the question: does this family is forced to have the finite intersection form? If it doesn't, you know what to do. Just put something trivial, like the bounded set, like the co-bounded filter. Otherwise, if it does, you just generate an ultra filter. This is the filter you put here. So the filter you have here, if it's a non-trivial coordinate, it will consist of this ultra filter chopped to this model, plus the generic sets you already added at coordinate alpha below D. Okay, and then this is the filter F alpha, and this is the force. Okay, this defines the entire forcing. And now what do we have to check? So obviously this is a CCC forcing. And now how do we get the set? So this is kind of the trick. We let I starts.
If I is forcing, itself is C6.
It's sigma center, yeah.
Oh, yeah,
He means
you're
big-
right.
He
Yeah,
says,
the five
he gets
over
filtered.
the all- So in the first case, what do you use? You don't use Matthias then, you just use some trivial.
I do Matthias everywhere, but in trivial cases, the filter I'm going to use is just,
Zero, what do you do?
so now it depends what oh yeah, so in the case zero, you can just choose a ground model ultra filter and do Matthias forcing over there, because I mean I didn't define it properly, but yeah, so but by definition, you should ask yourself whether X0 gives you a name for a ground model ultra filter, basically, and then you do Matthias forcing. Yeah, so let I be a set of be a maximal set, such that the collection of all alphas in I, so all the generic sets I added at index alpha, but for the entire row, I'm not allowing to skip anyone here, have the finite intersection point. Okay. So we don't, maybe I is empty, we don't know, but we claim that it's not. And in fact, that if you look at the B's indexed by such a maximal I, it is a VG ultrafilter. Okay, and here this is where we're also going to use the sigma directedness of D. I don't have time to prove it, but the idea is basically you take that set. If it has the finite intersection property, so you can extend it to an ultrafilter. You take a name for that ultrafilter. That name was guessed along using the diamond many times, and then you just pick a high enough point above I. So if you assume that I is bounded, you pick an high enough some places where the diamond gets the name for the ultrafilter above I, and you can show that you can add such an alpha to I, contradicting the maximality. That's roughly the idea. So what will be the eventual ultrafilter? Here comes, so there's a small trick here. This is why we did this specific diamond. You need to find a point alpha star, which is a limit point of I, of cofinality, the cofinality of mu, and that has mu many elements below it. That's not a problem, because you can just pick your element from the diamond sequence I enough. And so that when you take that ultrafilter that is generated by these sets and you cut it down at stage alpha star, when you cut it down here, you get an ultrafilter which belongs to that model. Okay, so there are club many. Okay, and that's going to be the ultrafilter. This claim that this one is going to be a simple PD point. And okay, you need to show that it's generated by these points. So we have some betas. They need to be in I, but by these sets. So each row you take all the sets, and they generate the ultrafilter you start. Also, you can check that this structure of nonlinear iteration ensures that whenever so if you take a point here, the Matthias set you added here is diagonalized by this one, but since by the nature of the iteration, if it's not below it, then it's not diagonal. It's an if and only if. That's the point of the nonlinear iteration. Okay, and finally, let's show that this is a simple PD point. So what we do, we basically have this D. It has cardinality in mu, so we can find a linearization of it. Like that. And then we enumerate I0, I1, and so on. In order so that and this is why I needed mu many elements below alpha star, and alpha star is the limit of them. And now basically I take the diagonal here, So we'll need a V. So I need the index I0, alpha 0, I1, alpha 1, and so on. And now you can show that this is going to be cofinal here. So the sets that I'm adding are actually going to be a filter base. And also you can show that the subset star relation on those sets gives you sorry, the less or equal in both coordinates here will give you exactly a copy of D. Okay, so that's it.
Sorry, another question.
Yeah.
So you mentioned Matthias forcing with respect to co-bounded filter. You mean for Sheffield?
Yeah.
So isn't that called coin
Not with a,
It's countable both.
yeah, you're right. Yeah, it's coin. Yeah, it's coin. Yeah, coin. I'm right. But just I could in the paper I think we say we don't do anything there, but just because I presented it where I start with the filter name, so I owe you a definition of a filter.
Okay.
But yeah, I could have just said.
No, I'm easy to confuse, but you're confused.
I'm sorry.
Why is it important? Is Matthias partial domain make sense for arbitrary filter? Sigma central or whatever it is. Why do you carry it to be?
So what do you ask whether we can just realize a base for a filter? This is, yeah,
Filter is okay. I mean, if you're saying properties of post made.
you mean
But in
here?
the end, he wants it all.
Sure, but there was somebody was telling you why is you are using Matthias over ultra filter. They don't need to be.
I didn't. I didn't use Matthias over filters. These are all filters.
That's what I objected.
Yeah. But at the end, we want to get an ultra filter, so it's important that there's all ultra.
So except for the view of the diamond, this is similar to Heckler's. Where he gets the omega and omega having a profile set size D. So I'm wondering, can you do this and not have omega having a profile set of isomorphic D? So what's the relationship between the profiling subsets with omega?
Well, I think that's kind of it's you can ask the question whether it's related to the question whether when you add when you do ultra filter of Matthias, is the real you're adding a dominating real? That's and that's I mean yeah, and there's this Kanja ultra filter, and I think you can maybe if you choose your ultra filter.
Then are you doing it to choose a Heckler? No.
I'm not considering this. I didn't think about that question, but now that you asked it, then it reminded me of it.
Naively, you might say maybe in Heckler's model you already have your result.
But there is a paper of Dordal in which he gets towers in P omega mod finite, but no unbounded sequences of the same length. And that's probably that basically. So just showing that they're very different.
Okay. Well, that's.
But there are I mean cardinal invariants which you will have there is a difference in cardinal invariants between Heckler forcing and Matthias forcing. So maybe this also points out that you don't get the same model.
They have different definitions. It's not always easy to get models where they are different. That's what
Yeah.
I'm asking about there. This method, might be so closely enough related to Heckler that it's you can't distinguish between.
Yeah, we should point out, I mean, we need to write down why you're right, that why in the Heckler model we don't get that. That's important to point out.
But you also said you would do this simultaneously for different directed sets.
I didn't do it. Mildenberger and Browninger.
Okay, no, that's it. Yes, okay. I see. So that's the only, like, I thought you had a general.
Yes.
So that's the only example.
Yeah. And just maybe if we already talked about this, well, we have that theorem. Well, it's kind of on measurable cardinal, you actually don't have these two cases. It has to be only one. So there is a difference between what's going on in omega, what's going on in measurable cardinals. You cannot realize the same thing. I mean, probably obvious, but it's one situation where it holds.
Can you say a word about the proof?
Yeah, the idea is that B kappa and D kappa, they have a nice characterization on uncountable cardinals, regular uncountable cardinals. Where did I write it? Here, proposition 3. It's using the club filter. B kappa is basically the character of the club filter.
Oh.
B kappa is the minimal size of
I see.
of collections of club which don't have a pseudo intersection. And now when you have a measurable cardinal, you can always Rudin-Kitzer project it to a normal. And then all kind of this, you get new ZFC inequalities there, which makes. That's the theorem. Okay, I went 3 minutes over the time.